do a Neumann problems. Junda, can you still hear me all right?
Yes, everything is right. Thank you.
Okay, so now we're going to solve these problems. We, make some noise from time to time, but I just don't. So you solve this, let's say, this boundary value problem, we'll do a minimization problem. I'm going to do just a Neumann boundary condition. Dedicated boundary condition, you can do some penalization method. So when I first looked at this a couple of years ago, I was wondering, as I told you, which I just do not have the space to cite many people, there's lots of people in the literature have tried numerically solving neural network for partial differential equations. And but I have not seen any analysis. And for a long time, I didn't know, maybe this analysis, I didn't know how to do the analysis. Because this is, for those of you if you do neural network in here, if you do the minimization in the finite element with me, basically you minimize these things in the neural network function space. So this turns out to be a highly long convex, long linear optimization problem. But it turns out now if you do the minimization, this is my neural network method. Okay, you minimize these things in this finite, this neural network space. You solve the minimization. That's my approximation there. That's my finite, what I call a finite neural method solution. So do you have, what is the error estimate? How do you do error estimate? It turns out, what is this? It turns out you can still prove the best approximation. And well, this is the reason is that even though the minimization problem 26 is highly long convex with respect to the parameters, but it's still convex with respect to V. So then you have these things. That's kind of like the classic thing. Then you can use this is a pretty satisfying because you can use whatever the error estimate you have gone before. The best one I've got is this very high order rate of convergence, but in this case it requires high regularity. Okay, so that's pretty much the error estimate for finite, what I call a finite neural method for partial differential equation for this elliptic equation. But there are lots of issues behind this thing. Before I get into this, but I just want to mention they have some remarkable superconvergence property. And the superconvergence means that take a biharmonic, wait a minute, what am I doing? This should be M equal yeah. 2m, the fourth order. There's a fourth order. This should be m equal to 2. This should m equal to 2. Fourth order equation. We know the Morley element is a quadratic. Quadratic, if you do the H2 is H to the H2 norm is H first order is n to the negative half. But if you do the neural network finite element method, is n to the negative 1. So you kind of get H squared, but you still have piecewise quadratic, okay? So if you do the Algarves type of element, Algarves fifth order, you can get H2 normally you get H4 n to the negative 2. But if you do the fifth order neural network element, you get it like H to the 8, n to the minus 4. So for some reason, the piecewise polynomial given by neural network has a much higher rate of convergence. So this is not only that. Even though the deeper neural network, let me just say, in this case, if you do deeper neural network, you have the funny looking space you still have the piecewise polynomial of some degree on a curved element like this, okay? As you can see, you can do error estimate as before, but if you go deeper, if you go more layers, that's one of the nice result. I have this here. This in this paper, they proved that when you increase the number of layers, you can reproduce higher order polynomials. What does that mean? If you increase the number of layers, you can increase you can actually reproduce a higher order polynomial. That means you can pretty much have spectral accuracy when you do these things, if you increase the layers. So if you do the reduced case power to do the finite element, you can one thing, if you take k equal to 1, I showed you before that it reproduces the piecewise linear function. Any shape. This means that you can highly adaptive locally. But if you increase the layer, you can reproduce all the polynomial. That means you can reproduce. You can also have global adaptivity. Maybe you can get a spectral accuracy. So it's kind of interesting. But these are the pure theoretical results. Now the question that how do you compute? One of the first things we ask is that you say, if you ever program, you have to do numerical quadrature, for example. You want to evaluate this integral. I missed a half here, I think. So you want to minimize this the interval. So you do the in this case you usually do we usually do numerical quadrature. And so I started to look at these problems, and so for many of you here have studied finite element, taught finite element. So you're going to go to the finite element literature to try to do it here. Then you soon realize you cannot do it. It's difficult. Actually, there's lots of people trying to do this analysis. There's tons of papers. I give you some examples here. But in most of these papers, you always, the analysis will all depend on some assumptions. And I ask myself a question, can I do an analysis without making any assumptions? If you make an assumption, you want to verify these assumptions. So in some of the existing literature, if there are some technique you kind of walk through, you make an assumption, the statement that, well, if the assumption is correct, my theorem will be true. But that is a reasonable thing to do. But I'm asking further is that can you verify all the assumptions? This is some of the things I'm going to mention this rest of this talk. So the integration you can in most of the machine learning kind of neural network kind of literature, people choose to use random sampling, like Monte Carlo, for example. You just or if you were a numerical PDE guy, but there's no point. Why don't we use Gaussian? If we could also do that. So, but you can either do random or you can do high order Gaussian quadrature, or whatever quadrature you do. So, if you do a Gaussian high order polynomial, you can do maybe depends if it's accurate for certain order polynomial, you have certain rate of convergence, and now the question that how do you do the analysis? It turns out when you do the analysis, you always need to, for the error estimate, for example, you need this high order derivative, to be, if you want to do Brown-Bell-Helbert lemma, do those things. When you do the numerical quadrature, how do you estimate this thing? But in general, when you estimate the things here, the high order polynomial in the finite element can be bounded by low order Sobolev space with some power of n in front of it. This is what we call in the Bernstein inequality, infinite element, we call it inverse inequality. And so if this estimate is true, then you can do some analysis. So actually there are some papers that are saying, suppose if this estimate is true, we can do the analysis. And so this is pretty much the standard approach, something you have to get around. But the bad news is that you make the assumption, but we prove that the Bernstein inequality cannot hold. And you can construct a counter example. If you take the Riluf example, you can prove that you can have this C of n cannot be bounded by a polynomial. It can be arbitrarily big. It's not so difficult to see because in this case, neural network function, if you can think about related to even this one definite element, can be highly non-uniform, can be heavily locally refined. In this case, the local element can be arbitrarily small, arbitrarily big. Hello? It can be arbitrarily small, then you can the inverse inequality cannot be held, cannot be valid. So that's bad news. So if you make an assumption like this, you better use something very special. You cannot use a Riluf example. So then we have to do something different. In this case, we're using this of a stable neural network. This is what this K1D, which I had before. If you use this kind of framework, then you can do some analysis. So again, you minimize these things. Now, basically, you want to say my solution variable, my PDE solution has to be in the K1D norm. This is one of those things which is for the PDE colleagues here, and in the old days when you do the regularity theorem, you do the Sobolev spaces, and for this business, we need to do the regularity in this K1D space, or the more maybe Byron space. So if they, of course, by if you have sufficient smooth coefficients at the boundary, and if you can prove that the solution will be in this Byron space, in this what I call variation space. And so you want to minimize these things only within this bound. If you have to do this, if you do the numerical quadrature again, you also do the things in this function space. The nice things about these things here in this space, this space is quite smooth. The K1D is actually in the WK infinity. It will be bounded. I just want to emphasize here at this time of the business, I'm happy to do any analysis, but in this analysis, I'm going to require my solution to be quite smooth. So if you do that, but again, if the K1D space, in this case, the solution is quite smooth, and the WK infinity is actually bounded. In this case, you can do the numerical quadrature. For example, you do the sigma value to the case power, and so you do the n neurons, and you can prove that you do the minimization problem here. You take the numerical quadrature point. If you do the Gaussian, you get the optimal rate of convergence. One thing which I didn't mention last time here, that if you do the cosine network, you don't have to do the reload to the case power. The cosine, for example, you can prove arbitrarily high order as long if you have smooth. It's kind of a spectral method. If you do cosine neural network, it's kind of you have spectral accuracy. The smoother you have, the better rate of convergence. And you can even get exponential convergence, but I'm not getting into those details. So if you use this variation space K1D, you can do analysis. So there's a proof here. It's not the most interesting situation. This proof is pretty much like the classical analysis, and so I will not get into much details here. So, but the main thing is that you want to get the theoretical things to be correct. You want to stay in the correct functional class. Fortunately, of a approximation theorem, which we have recently I did with my postdoc, Jonathan Segal, and some other postdoc like Qingguo, Hong, and some other people. The theorem we have this actually is paper. So yeah, this is in particular this paper here. I think we submit to the MATH-IMS, I believe. And we have all the rigorous analysis there. The first author here is Hong Qingguo, and the second the second is Jonathan Segal. They're both my postdoc here at Penn State. So this is for the Gaussian quadrature. Okay, now one of the things here for numerical PDE, why do you ever even use a neural network PDE? Is one of the interests of high dimensional problem. High dimensional problem, numerical quadrature, you don't want to use Gaussian. That's too expensive. So you can do some sampling. The sampling, of course, you do some sampling. Now, one of the things that how do you do the error estimate of the sampling? This is this is kind of related to this what we call this the generalization accuracy, right? If you have integral, okay, if you have integral, you want to do some sampling, and you do one sampling. When we say generalization, you do the expectation. In this expectation, under such a probability distribution, do some sampling. You have some, so this you take all the expectation with respect to the sampling. That would be pretty much the expected generalization accuracy for the numerical quadrature. Yeah, there's a classical result. I was tracing this literature. We could trace this for about 20 years ago. It can be bounded by this so-called Rademacher complexity. In this machine learning business, you have Rademacher complexity, V3 dimensions, all this classical analysis. In this particular case, we use the Rademacher complexity. This is pretty much kind of is a quantification of the richness of these functional classes. And this is because that is a random variable which takes the plus or minus 1. The xi, you do the sampling according to a certain distribution in the domain of your interest. And so this is called Rademacher complexity. And this is a classical result, which we're going to use. Now the question is that you have to estimate this Rademacher complexity. It turns out in this paper with this careful analysis, you can get with this dictionary generated by this ReLU to the case power. You take the gradient, the Rademacher complexity. If you're sampling n points, capital N point is n to the negative half. It requires some very careful analysis. And so you put this together, this is what we call one of the keywords in machine learning is that it's a so-called generalization accuracy. But in the final in numerical analysis, in something we're all doing some kind of generalization accuracy analysis. In this particular case, if you compute your neural network numerical quadrature by certain sampling, use the Monte Carlo method to do the integration, then you do the minimization like 44. The best thing you can do is with expectation within this same distribution sampling, what kind of error you can get. It turns out you can get to n to the -1. This result is a K1D result. You can and you can do the numeric n to the -½ with the numeric quadrature. So you can prove a theory like this. So that's satisfying. You can get we have lots of error estimate. This is just some examples. So you have the original PDE. You want to do some minimization problem, but the integration has to be computed somehow, the numeric quadrature. There's one more big thing. Not only the most difficult thing is how you actually going to solve this optimization problem, huh? And how do you solve this optimization problem? Even I take again, there's a lot of paper in the literature here. If you take a given any function, for those of you who want to study this problem, take any function x sine square, sine x, cosine x, x squared, take all this. You want to try to fit this given very nice function by some neural network. You will be disappointed. If you try that, you find that you really cannot get a good result. For I'm sure many of you, I see quite a few people in the audience today. And if you want to, one of the most popular methods used is the SGD or maybe some variation Adam method. And it has been extremely difficult for us to see if you increase the number of neurons, if you use your optimization to get some kind of a asymptotic rate numerically. When we do finite element writing paper, some have certain h to some power and all that, but in this case, maybe n to some negative power, we proved that, but somehow I have not been able to. I do not know anybody among the people I know who have been able to use Adam or whatever method to get some asymptotic, cis asymptotic on the 48. I don't know if Zhou Jun, can you hear me? Hello, you guys hear me?
Yes.
Hello?
Yes. Yeah.
Is my question make sense? Do you understand my comments here?
Yes.
So you have a beautiful algorithm here, you just cannot compute. Well, I'm going to address these things a little bit. So here's the deal. The numerical, this yellow line is you maybe enter the -½ you go down, but if the neuron increases, they call it neurons, okay? Because but if you do all this traditional method, this machine learning method, it's gonna get a flat. You cannot decrease. Just I don't know. Maybe we have not been able to tune our code, but anyway, we have I've been asking around and it seems to be difficult to get it. Anyway, this is a very tricky, very expensive algorithm. If you in some of this paper, if you reproduce the code, it takes hundreds of thousands iterations. At this stage of the game, and the complexity is, I'm not even asking how much it costs to do it. I don't really just to run your computer. Just give me some numbers. Even that is difficult to get. As a mathematician, it's kind of annoyed by these things. Well, the accuracy in practice, you can pick up 10 to the -3. I don't know, still be good. But now you want to get 10 to the -2 to the -4, -6, then that's easy. So we actually recently studied these things. Actually, It's kind of, we're trying to use again, optimization for this type of problem is the challenging part. There's something called a greedy algorithm. How I'm doing with my time again.
10 more minutes. Yeah.
Okay, so I better hurry up. So there's something called a greedy algorithm, and the greedy algorithm is that every time you kind of add one kind of neuron in there, you do the Marx problem. This one it has to do with the dimension of the dictionary, the 50. It's still optimization problem to solve. In two-dimensional PDE, it's a two-dimensional, two-variable function optimization problem. But if you do these things here, you know, there's quite a large literature in statistical approximation theorem community in different contexts. But the orthogonal, this greedy algorithm, they usually do the n to the negative half. And they also something greedy, relaxed greedy algorithm and all that. We actually have done quite a few things on these things with Jonathan here. And in terms of the orthogonal greedy algorithm, we can actually, the traditionally only get n to the negative half, we could get a 2K, get the extra power, which is the optimal rate of convergence in the in this K1D space what we've been doing. So this is the kind of surprising to some of the people who work in this business, and we are the first one who actually using so-called greedy algorithm to produce kind of the best. In the existing literature, they only do the n to the negative half. We could do reach the optimal power. But anyway, we're going to use this thing to solve the PDE. So you do these minimization problems. You can prove that you can get to the. Well, there's some technical issue here because we have this things called stable neural network. And so you want your training algorithm still stay remain in this thing. This is called relaxed greedy algorithm. Turns out to be you have some converse combination, and it turns out it's in that category. So we use this to prove theorem like this. You do the minimization problem, at least you get a target function to be close. So you put all this together. So not only you have the numerical quadrature, first of all, you have the error estimate without the numerical quadrature, then you have the errors with the numerical quadrature. Then you have to have an algorithm to achieve that. So if you use gradient descent method, you can never achieve that. At least I have not been able to do that yet, even numerically. Not to mention you can prove anything. You just cannot prove anything about it. But here we have a provable result, which is to reach a certain level of asymptotics. In this paper, I wrote with Qingguo and Jonathan. This is one of the theorems. And but again, in this particular method, you still have to do a optimization problem. In this case, this dimension D, if you solve a two-dimensional, three-dimensional problems, basically you want to solve this optimization problem for 2 or 3 variables, which is not too bad. But if you do a high-dimensional problem, then it becomes a challenge. And we still have to work on these things. There are some greedy algorithm has been studied quite a bit in the statistical literature, but we're using here solving PDE. At least you reduce to maybe if you do a number of parameters, the neuron, if N is 1,000 neuron, you have to solve 1,000 dimensional optimization problem. Here you solve maybe 2 dimensions, 3 dimensions. If you solve both one equation, maybe 6 dimensions. Anyway, still issues, and but we do not know any other method. This is the only method we know. So we have, as I told you before, if you do gradient descent without, you don't see any asymptotics. But then when you use this greedy algorithm, we can observe all the theoretical asymptotics. All this numerical tell you that the theorem we have proved, you can also numerically realize it. But in comparison, for example, this plot I was telling you is that you see that in the SGD or other methods, and you just don't get it. After a while, you just get stuck. You just cannot. Again, maybe we have not able to tune the code, but we don't know anybody who has been able to do that. But anyway, so we have this examples which you can verify of a theorem. You can also compute some example which you do not quite prove it, but nevertheless you can still observe some convergence. I think my time is running out. And I want to make some conclusions. I mentioned that in the earlier part of the lecture, we say when you do the ReLU activation function, the ReLU DNA is really linear finite element method. As a function, but they have utterly different structures. In particular, the error estimate is so much better. And for sufficiently smooth function, linear finite neural method has no curse of dimensionality. Basically, you can, if your function is to be in this variation space, but when you say no curse of dimension, we have to be careful. Your function, make sure that it's in the right functional class. And but we actually can prove a certain class of functions satisfy this property. Then this piecewise linear function based on neural network has no curse of dimensionality. But if you do linear finite element, you cannot do high dimensional problems. Again, I mentioned the finite neural method has superconvergence properties. But how do you actually realize the superconvergence property is still lots of issues. Again, for high order PDE, I said the high dimension is 1K. You have the potential for high dimensional PDE. For high order PDE, it's kind of interesting to see that it's pretty trivial to do a low order polynomial for high order PDE using neural network. Well, in finite element, tradition is very difficult. It's very high order elements. And but despite of this interesting theoretical result, but it's still a nightmare to actually solve this optimization problems. And well, you can get always, there are lots of paper reported nice results from practical point of view. But if I ask a theoretical question, if I want to make sure, the error to be smaller than 10 to the minus 3, can you do it? You can do it, but it's just pretty costly. But anyway, but of course, I just want to comment right now here is that there's still, despite of these things, it has lots of, as a research topic, there are many theoretical issues. And the practical challenges means that we need good algorithms. And especially for high dimensional problem, we have all the theorems to point in that it has potential. And there's also empirical results to seems to support that claims. But theoretically, you have to say a PDE, for example, you have to, your functional class, your function to be approximate should belong to a certain functional class in order to. But the keyword in this business is not to use these things as a numerical PDE tool. Is the machine learning approach to solve the PDE. What does that mean? Suppose you solve the same kind of PDE for hundreds of times. I don't know how many, for those of us solve PDE for a living, especially for practitioner, either you solve it as a statistical equation, maybe now a Stokes equation or Euler equation, or maybe a Maxwell equation. Suppose you solve the same kind of equation hundreds of times, thousands of times, you remember that. That's what we call a training data. And so you can also use machine learning neural network with or without neural network. You can solve what we call offline calculation. In that case, maybe the cost is not the major issue, but you can let your computer run this for a month, like maybe I don't care. But you train the network when you have a new data to come. You namely, if you since you're, especially when you do a design, maybe you do airplane design, car design, you make you do a lot of simulation, you make maybe a small alteration in one place or another. So all these different computation are very similar. Those are the kind of the training data you use that one. So if from there you can, when you have a new configuration coming in, you kind of use your training neural network to have the inference. Where many people would kind of, my computation is 100 times, maybe several order of magnitude faster than existing code. The secret here is that there's hundreds of thousands, maybe hours in the backdoor have done some training calculation for similar kind of problems. But this, I think, is probably it's a fantastic, very exciting research field to do, and using the machine learning to solve a partial differential equation or practical compression, airplane design, shock captures, all this stuff, and has a tremendous amount of potential. There's a huge family of theoretical issues to be worried. But today, my talk is address some very simple issues. Again, this is a very dynamic research field. All the different people look at the things from different angles. For me, some numeric analysts like me, I want to look at some of these things from the rigorous mathematical viewpoint to see what you can prove, what you can analyze, what kind of algorithm you can do. Hopefully that provide some kind of understanding of this vastly, extremely active research field. Hopefully this lecture will has given you some ideas of what's going on here with this type of problem. And that I'm going to stop here. These are some of the paper we just finished. It's some of the online, something we're still trying to write it out. Thank you very much. I'll just stop here.
Okay, thank you. Thank you. Really, so we'd like to thank the speaker for the very inspiring and exciting talk. And you have really showed us a lot of very constructive relations between the neural network and the machine learning type of algorithm and the modern approximation theory and numerical solutions of PDEs and so on. So now let's, so questions, comments from the audience? So we have a huge audience. I suppose there are quite many interesting questions, comments from the audience.
Yeah, so can I ask a question?
Yes, Zhonghua, please.
Yeah, so Professor Xu, very nice talk. So
thank you.
So can I ask a question on the adaptive finite element method? So that's very useful for some problems with some similarities. But for this neural network method, do you have some comment on this kind of adaptive finite element applications?
Yeah, the very good question. Thanks for asking. The secret here is that all this business of the neural network, even in the machine learning, AI, all the secret, all this work is in the training algorithm. So the training algorithm, I talk about the greedy algorithm, SGD. One of the theorem I proved in the first lecture, or maybe I mentioned here earlier, is that By increase the number of layers, the reload DNN, it reproduce all the finite elements in the world, any different crazy shape. So in theory, it will automatically adapt anything. It's the best adaptivity you can ever think if you can solve the optimization problems. And not only adapt locally, it also adapt globally. It adapt, you can do mesh. If something is smoothly through some high order polynomial, if you do some local singularity, you will get the refinement there. But that's only in theory, not how to do it. But if you minimize this minimization problem, you really find a global minimizer, you will get the best possible adaptivity. Let me tell you that in finite element method, so-called adaptivity is a fake adaptivity. Oh, I shouldn't say that. I have done that. It's called a greedy adaptivity. What does that mean? Adaptivity, you can really think is you can treat the finite element, the vertices as unknowns, right? If you treat them as unknowns, you motivate. But what do we do in finite element? You give a mesh. So you use as error is you move the mesh a little bit. It's a type of greedy method, adaptive. You can maybe add some elements and remove some. It's not a truly a fully adaptive method, but that's the best way you can do. So in deep neural network, the fact that I can reproduce for the linear case, any linear finite element. So you can do a deep layer. If you can solve the optimization problem, my friend, I get the best possible adaptivity. But training algorithm, optimization algorithm is the whole key. And so the one thing that you can do is there's I spend quite a bit of time in the machine learning, classification of that kind of stuff. They said I'm going to have my maybe resonate some other structure of neural network. This one has better generalization. I can tell you, it seems to me, it's not because of the structure or your model, your fancy hyperparameter you're tuning. It's because of the way you do the optimization, you can get something. So optimization, training, all this has so again, this is a very critical, important question you're asking. And the theoretical answer is absolutely yes. Practical answer, I don't know. I just don't know.
Thank you. Thank you. Thank you for the comment.
Yeah. Lots of potential for sure.
Yeah, some questions in the chat box. Can you read?
Yeah, for problems on smooth solution or noisy data, can we observe similar nice convergence result numerically from the solution provided by the neural network? And I have you can again, as I mentioned earlier, that if you do deep neural network, you can work hard enough for the non-smooth data, and you in principle see that in 1D I can do that. In multi-D, you will have some initial success. Again, it's the optimization problem that bothers us. In other words, thank you. Could you explain the idea a little bit, combining greedy algorithm and the neural network? Does it mean that we add some neurons inspired by the greedy? Yes, you just adapt to add neurons. It is if you have n neurons, you do n steps. That's roughly speaking, and it is it's an algorithm that usually in the optimization and in the statistical quite a bit. And again, this 现在是没有办法中的办法，这个 but anyway, but we can actually prove something, and we can numerically see that. And I'm actually always I've been telling, okay, my specialty is doing fast algorithm. I'm actually I'm working on this in the beginning of this thing. So we are doing some slow algorithm, but I want a system convergence. We desperately need fast algorithm, which we're too busy right now to doing the more trivial stuff right now. And yeah, the greedy algorithm is one of those algorithms. Greedy algorithm, you know, the greedy is not a great word, but in computer science, greedy algorithm in Chinese, I don't know how you translate. 贪婪算法, greedy means you don't care for other people. That's why you're greedy. That means local optimization. The greedy algorithm, you just do local optimization. Every time you do a little bit. And yeah. Does a greedy algorithm perform better than SGD and Adam? I would say yes, for the problem I have tried. I would for this which friend is asking this one. Anyway, try the Adam method to do the system rate of convergence. You want to increase the number of unknown neurons to see if the error will decrease. So far, we have not been able to produce any interesting result to see the decrease. But for greedy algorithm, we can do that. It's still expensive algorithm because you still have to solve a one-dimensional, two-dimensional kind of optimization problems. And you're given a three-variable function on a cube. How do you find the global minimizer? That's a calculus problem for when we, you know, if you do multivariable function, you solve, okay, I'll give you a cube, a unit square, you solve two variable function, find a minimizer, global minimum. Well, you take the stationary, you can do that. If you give an arbitrary function to find the global minimum, it's not so obvious how you do it. But you know, yeah. So maybe anyway, the answer to your question that about the Adam, I don't know if I say that. So for Adam method, we're not able to see the asymptotic, but for greedy algorithm, we could do that. So the second, the next one, can increase the depth of the neural network greatly improve the accuracy? And this is a very, very good question. And for renewed neural network, for example, in the machine learning, there's something called the deeper the better. And the deeper the better is that the ReLU neural net, for example, in principle, the deeper is better indeed. For ReLU especially, ReLU has the property that reproduce identity. ReLU reproduce identity. So like, this means what? The deeper, well, as a functional class, is a richer functional class than shallow. All right. Theoretically, the deeper the better because the function class becomes bigger. It also becomes in the finite element, which I talked earlier. If you do real DNA, if you have to have sufficient many depths to reproduce all the piecewise polynomials, piecewise linear functions. So yeah, so the deeper, not only deeper the better. If you want to really have the full capacity, especially for long smooth functions, you need the deep. But in theory, deeper the better. But again, you have to train it. You have to be able to solve it. Practically, the results can be mixed. Okay, I don't know if that. Yeah, that's my answer to your question. If the equation is non-linear, like one incompressible flow, what technique can we separately change the activation function, increase the depth? What techniques can we do to improve? So for the compressible flow Euler equation, for example, here I did the elliptic equation. You do the so-called energy, but for the general nonlinear problem, you can always you know, in the literature, what they call the PIN, PINN, the physics informed. What they do here, you take a PDE. You just look at the residual, for example, it's pretty much a least square. You use like activation, what they call the loss functions. And how do you improve the accuracy? You do not necessarily change the activation function. We have proved the theorem before. Basically, any activation function will give you something reasonable. But I like the people like ReLU for many different reasons. One of the reasons I mentioned earlier, ReLU reproduces identity. That means from strict mathematical things, deeper is better, deeper content. So how do you increase the accuracy? You increase the number of neurons, the width, what they call the 宽度. And you can probably increase the layers, that's the 深度, the depth. So that would increase the capacity of your function classes. And certainly, but now all the name of the game is in your training algorithm. Like Zhonghua, you asked earlier that can you do adaptivity? In theory, you can do adaptive perfectly. But again, you just have to be able to be able to solve this optimization problem. In theory, you can. In practice, we you know, it all amounts to how do you solve this, minimize this loss functions. Let me see. 请先问离散得到数据，然后神经不是增加了复杂度吗？先离散得到，然后用神经网络。I do not quite understand this question. 先离散得到数据，周军，你帮我读读这句话是啥意思
？I think they may have some misunderstanding. The thought, the data that you get is from the discretization. You solve the discretized system and then get the data.
So they are, okay, that's a good question, but I think the machine learning, which people get excited because you can get data many different ways. You can get data from experiments, you can get data from the lab, you can get the data from computation. You put all this jungle together. So that's what we call training data. So from there, you build some neural network model. Does that increase the complexity? Yes, absolutely. This is going to be a tremendous deal. But then the argument is you can do this so-called offline calculation, you know. You can, this kind of, you done that, and also you can do a transition, what we call transfer learning. If you do these things here, the next time you have new data, you can use this one. So it's kind of ongoing things. And complexity increase, yes. And the efficiency of your machine learning model, maybe because the more training data you have, the better of inference generalization accuracy you will get. But it's also more complicated, more expensive to train. Would auto convergence rate be larger with a deeper DN, or just the constant part of the convergence be smaller? So this is a very good question. Let me just give you example for if the solution is very, very smooth. So so you have certain rate of convergence. The other thing is that if you think of relate to the piecewise linear function finite element, so if you increase the depth, the neural network becomes more adaptive. It becomes more local refinement. So in that case, the deeper would get some high order convergence. So that would be some answer to your question here. And let's see, ReLU as a piece of linear function is not very smooth. Does the smoothness of the activation function affect the accurate and the optimization difficult? Very, very good question. You may wonder why people like to use ReLU so much. ReLU is not very differentiable. And again, I have this this ReLU to the k's power. If you raise the power of k, it becomes smoother. And you can see the rate of convergence I provided for the shallow neural network. That's the optimal convergence rate for the stable neural network function. So by increase the power, the smoothness of the power, well, the smoothness of k, the smoothness for the ReLU, not only increase the smoothness by the square or cubic, it also increases the kind of a degree of polynomials. And in that case, you do increase the rate of convergence. And does it help you to to train? You know, again, you can say, for example, you can worry about that. You know, many people, you know, especially when you do PDEs, I still don't know why people only use the SGD. You may think about doing Newton's method, some other method. But the machine learning people use SGD because SGD generalize well. It's very important in this business that there's something called generalization accuracy. If you just solve one given PDE, of course, you do the other stuff. So now, again, the answer to your question is kind of mixed. So if you use a smooth function, you're allowed to use a higher order method. For example, Newton's method, you may be able to take a Hershey matrix, right? And but the problem is that you don't know where the global minimizer. You know, you have to. So a high order method in the beginning may not help you to get anywhere, but once you get to the convergence, maybe to getting close to the global minimum, you can probably high order method will work. So this randomness sometimes probably help you to find the global minimizer in a larger probability. Or it's an issue that which many people are still studying, and that's. Yeah, okay. I think, did I answer that question? Yeah, I think I did that. But sometimes more depth leads to overfitting. Is there any optimal number for depth? Very good question again. There's a big mystery in machine learning. In the machine learning, especially the AI optimization problem, you do the convolutional neural network, and there are much more parameters than data. These days you have this transformer that have a huge number of data, but that means you have very rich functional class, a lot of parameters. But it's one of the way I say machine learning is an interpolation problem. You have used a polynomial for 100,000 degrees, you only interpolate 20 points. So what the generalization means? Generalization is accurate with the point which is not interpolated. So it means that if you have lots of parameters, but you don't have many data, you have to be overfitting. The overfitting is automatic. Overparameterization, few data, you definitely have overfitting. But why you don't have overfitting in machine learning? It's a contradiction. It is because, again, the secret is in the training algorithm. The stochastic, you would really never solve the problem. You solve the problem to some places. So, so this is the key word is regularization. Regularization, basically, if you have a large functional class, when you regularize, you make the functional class smaller. You want to regularize it to be the right amount. It's just fit the data well, that you just don't overfit. So this stochastic gradient descent method has this built-in regularization effect. You do not want to solve too accurately. If you solve too accurately, you do overfitting. So the number of parameters, this also answer your question of the depths. You have more depth, and the more depth, the function representation power of your network is bigger. But again, you have to bring in more the appropriate regularization so that you generate well. So again, all the secret is in your optimization algorithm. And that's my answer to your question. What is the optimal number of depths? I don't know. Nobody knows. And but again, everybody has different experiences. But again, it depends how you tune your parameter. How do you use your optimization algorithm? All right. The neural method works effectively for time-dependent problem. Is there any new challenges that you realize? The challenges are everywhere, and and time-dependent problem, in principle, my analysis is actually based on the energy minimization. The machine learning in most of these 万金油 you can do any equation. You can just look at the residual, do a collocation, or do sampling, and analysis. Good question. Analysis, you can do a hand wavelength analysis, a lots of analysis in the literature. But if you want to make everything rigorous, there's already a lot of work out there. It certainly has another variable you want to worry about, and there are already many papers on this topic. Again, many of these papers are written based on some assumptions. But so to verify those assumptions, all the things are all many ongoing work. And I choose this simple problem to work on because this you can be more rigorous. And I believe the time-dependent problem you can do as well. And again, there are many existing work on that kind of problems. I don't know. Did I miss any problems, Dugan?
Yes, I guess there should be more questions from the audience. This is just some questions from the chat box. Yeah. Okay, I guess it's already a bit late to you. And maybe, yeah, so if there are more questions, you may send emails to Professor Xu, yeah, so that he can answer. Yeah, can I maybe, so give one question?
Yeah.
So basically, you're talking about the superconvergence and so on. And you mentioned that for one specific finite element method, actually, if you combine with the neural network, and then you can get much higher order of convergence. Now, my question is, let's just look at one variable. So the most, I mean, the problem that you like most, actually, you are real expert for the problem. That's, for example, the second order elliptic interface problem. So where we have basically we have only piecewise H2 regularity of the solutions. Now, do you know, or are you aware, any neural network, machine learning type algorithm that can beat really finite element method?
I don't know what you mean by beating, but
I mean, they just convergence order, and plus, of course, we have to look at the efficiency.
Let me, if you talk about the order of convergence, because I told you that the deep neural network reproduce all your finite elements. So whatever you can do, my neural network can do. Okay?
But you have to realize, yes, you have to implement, yes. How to implement that?
Implement is a nightmare. So if you want to implement, if you take your interface problem, use your finite element or finite difference. Don't use your network. but I don't know, especially for low dimension problem, I don't think anything can beat what we know before. But of course, at this stage of the game, the interesting thing about this problem is that we cannot make conclusion too fast, right? Because it is pretty in the early stage of its research. And what I do mostly I'm just having my theoretical curiosity, but I don't know. And I'm just curious of what's going on. But I do the best I can for this analysis. But this assumption, the smoothness assumption, is still very too strong. And the optimization algorithm still takes a lot of time. And it's the beginning. Whether this is only going to lead to something exciting, we don't know. But one thing I know for sure, the machine learning part of it in the end, I believe that's the way to go. And but to understand the machine learning, I think we should begin with the exercise I just did in my talk. And we also proved quite some new theorem recently along that direction. And there's again, this field is so vast and active, and there's so many results out there. And so to to meet your requirement. Wow, accuracy, efficiency, and it's the comparison. Ultimately, I believe is the machine learning part. If you solve the similar problem many times, next time you have a new problem coming in, it's going to be very fast. Maybe in the background, I use hundreds of hours, but this time I only a few seconds. So, so the comparison is kind of different game. Anyway, it's a good question to ask, and that's the best answer I could give now.
Okay, thank you. Yeah, thank you so much. Thank you so much. I mean, this is wonderful talk. Thank you again, and also we thank the audience, okay, for attending this wonderful talk. So thank you all. So welcome you next time to this sequence of talks. Thank you very much.
Thank you，再见。
拜拜。
郑超，
哎，
太好了，非常好啊，谢谢你啊，这是非常 exciting，呀，what exciting，呀。
好，再见，再见。
再见，
哎，再见，好 ，OK， 谢谢啊，谢谢你们来听啊，感谢。怎么，郑超什么时候有时间回香港啊？
你要隔离多久啊？现在要隔离多久？现在在香港的最新政策隔离多久啊？
好像是还是3个星期吧。还是3个星期，太长时间了。
你让我们周老板去给你申请一个不用隔离的，周老板去给特首打个电话就可以了。
哎呦，有这样的办法，那真的是好啊。
这里有办
法。周斌，你有这个办法？周斌
啊，
你有这个办法可以不隔离？
你有啊，你不是跟特首有特殊关系吗？
要找一下，要找习主席开一下后门，可能可以。
对，要找习主席才有可能啊。
不过我觉得这个疫情应该快过去了吧 ？I hope. I don't know.
哎，现在看美国的情况好像是下降很快嘛，对吧？
得病的人也很多，但是也没事儿，得病就
对，关键是得病的人没事，咱们把它当回事儿。
对，现在基本上当做